तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so today we will see on systems of rigid bodies, supposing there are forces and moments acting, how do I find out equations of equilibrium. I will focus mainly on planar rigid bodies. Okay, I am going to give a few tricks that you can use in order to solve problems. Okay, and from a problem solving angle only I am going to look at this particular session. To start with, let us examine a planar rigid body, okay, subjected to various forces, let us say F1, F2, F3, F4, let us say there is a couple here, MA and so on. Okay. One thing that we already know is we can convert this into an equivalent rigid body, or a body, or this body with, so we know that we can write an equivalence of these force system on the same rigid body as a resultant force acting. So let me call this as F. Okay, all these are vectors and a resultant moment, let us say this is point O MO, alright. Now over this we have to apply the condition of what is happening to this particular body, is it moving or is it stationary. Okay. Let us look at the first question of it being stationary. Okay. If it is being stationary, we say that the acceleration is equal to 0. It is a principle of statics that we use right now. It is not rotating, which means the angular acceleration is 0. It is not moving in the x or y direction, which means those two accelerations are equal to 0, and if we apply the principle F equals m a, mind you I am writing this as vectors, this m is the mass of this particular rigid body. If this is equal to 0, we get F equal to 0, and this is one equation. The other equation has to do with the moment is equal to I times alpha, where alpha is the angular acceleration of this rigid body. I am just writing it as scalar, but it is something that is about an axis that is perpendicular to the board. Okay. And this is also equal to 0 in a condition of statics, which means we get these two, mind you, these two vector equations. This is only one particular direction, and therefore we are just going to make it a scalar equation, and this will have two components, the moment we give an x direction and a y direction. Okay. And therefore this will simplify to F equals 0 will imply its first component Fx equals 0 and the component along y direction being equal to 0 and the moment about O equal to 0. Okay. Fx and Fy are components of this vector F, which is a resultant of all these forces put together, which we have already seen. Okay. And this is a simple procedure. We can find out the relationship between the forces and moments by solving these equations. We can solve for these values once we know the forces acting on the body. Okay. So let us look at a simple example. Supposing I have a body which has a force F acting like this, okay, along the horizontal, and there is a particular point here which is hinged, okay, and there is another point over here which is a roller support, and I wish to find out what will be the resultant force, resultant reactions that will come onto this particular rigid body. It is a very simple problem. The first exercise I have to do here is I have to now represent all these constraints that I have here, which is the hinge constraint and the roller constraint, as forces that take part in this constraint, okay. We call those as reactions. So in this particular rigid body, this hinge will offer two reactions. I am going to represent this as x and this as y. So I will have one reaction like this. Let us say this is A and this is B and this is point C. We will have a horizontal component of this, so let me call that as Ax, and there is a vertical component of this reaction Ay, and there is a particular direction to this. So let me just represent the direction, okay. Let us say this is around, this angle is theta with respect to vertical, so I can represent this as the force B, okay. Mind you, in this particular case I know at what angle the force is acting, which means only the magnitude is an unknown. Here the two unknowns are Ax and Ay, okay. So if I complete it, this shows the free body diagram, okay. This free body diagram is essential in order to solve for the unknowns using systems of equations, okay. So let us write it down. If I am looking at statics, I know that each of these components the resultant components have to be equal to 0, okay. So I have to convert this into, for the same rigid body, assume this is the same rigid body that I am drawing, I have force here, force here, force here, force here, and a force over here. Let us say the resultant force is acting like this, and this is vector F. I am taking a point over here which is, let us say, O. We will come to what point to take at a later stage, okay, and a moment M at O, okay. If this is stationary, the force should be equal to 0, the vector itself should be equal to 0, or Fx Fy should be equal to 0. Let me just change this to P so that we do not confuse between this F and that F, okay. And this m naught, which is the moment about an axis that is coming out, is also equal to 0, alright. How do we write F? F is nothing but, we have these forces Ax acting along this direction plus Ay acting along this direction plus B, which is acting along a direction that is theta to the vertical, plus F that is acting along, I am sorry, P that is acting along horizontal direction. Mind you, it is a vector equation, okay. I have to now separate this into horizontal components and vertical components. Alright. The other equation, so if it is stationary, I have to say this is equal to 0. Okay. The other equation tells me that m naught should be equal to 0, okay. M naught I can find out by, let us just do that exercise. I have a force P over here. If I have to find out the moment of this P about this O, what is the relationship? Let us say this is the point, let me call this point as 1, okay, and let us say this is r, a vector r, then the moment about this O for a force P can be given as m is equal to r cross P, okay. In this particular case, since it is just a planar problem, if I find out the perpendicular distance here, let us say I am going to call this as d1, then this is simply, the direction is going to be like this. If I hold some object and pull it this way, it is going to rotate like this, that is an understanding that I can have, and therefore I can say this is minus d1 times P, okay. P is the value of this force. I know P is along the horizontal direction, okay. So it is primarily P x component of P, okay. So like this I can find out, this is MO for the first point, we will have to do that for the other force B, the force AY and the force AX, okay, and then insert it over here in order to get the relationships between these forces, okay. One more important thing to understand here is I wish to tell clearly which is the direction that is assumed to be positive. If you go back, we have used x positive direction to be like this, y positive direction to be this way, and if I take a vector that is outward to the board, that is a positive direction. So if I have a vector outward, the moment is going to be anti-clockwise, which is taken to be positive. So one way of doing this is I can write Fx, or the component of this force along x direction, which is this positive, is equal to 0. This is a positive quantity, this is equal to 0. I can do the same thing over here, m at O taking anti-clockwise to be positive is equal to 0. By doing this, we will not miss out on the sign conventions. For example, in this particular case, this particular force P is trying to rotate about this point O in a clockwise direction, okay, which is negative of anti-clockwise, and you can see here d1 is a positive number, P magnitude is a positive number, which means I will have a negative sign over here indicating that it is actually a positive clockwise value represented by anti-clockwise, okay. You can do the same exercise for each one of these. One of the advantages of planar problem is all I need to do is to find out the distance of the vector direction to a particular point in question. For example, if this is the body, if this is the force B, I can extend this line, find out what would be the perpendicular distance of O with respect to this B, okay. Let me call this as d1. Again, if you notice, the force is such that it is acting to rotate the body in the clockwise direction. So I will get a negative value when I insert it in this particular thing, okay, and this is how I can solve the problem. In the examples we will have a few problems that we will tackle, but before ending there is one important trick or principle that we should know. Remember, whether the force is over here or the force is over here, the moment of this force about O will remain the same, okay. So even if I had put the force over here, let us say this point is 2, I would have gotten the same moment, okay. So it is only the perpendicular distance of the force at a part with respect to a particular point that is important to us, okay. And in a similar way here, it is simpler if I write it as Ax and Ay because the distances that I can find out for this, for example, I am just going to erase this and draw fresh so that you understand how easy it is if I write it in terms of components. Okay. So, if this is the body, if I take this force P, I know this is a horizontal force. Okay. All I need to do is to find out the vertical coordinate difference between this point O and this point 1, right, and this y coordinate of 1 with respect to O will immediately tell me that is the lever arm, or that is the arm that I have to use to multiply with the magnitude of P. Okay. And similarly, if I have split this reaction into Ax and Ay, it becomes easy, because all I need to do is I have to find out the difference between the y coordinates of this point, let me call this as 3, between the coordinates y coordinate of 3 and y coordinate of O, or in other words this is y3 minus yo. Okay. And then I can multiply that with, I will take this magnitude multiply with this Ax. Again, to make it very simple, I will physically look at what the direction is. If this is the positive distance and this is the way the force is acting, it is going to go anti-clockwise, which means in this particular equation I will have it as positive. Okay. So, in that sense, if I write, this will turn out to be Ax times, let me call this as y03, okay, y03, which means the distance between, I am sorry, y03, distance between O and 3. Okay. This is a positive sign because it is going anti-clockwise. On the other hand, if I take this one, it is going to go clockwise. So, I will have a minus Ay times, right now I have to look at the distance in the horizontal plane, horizontal direction, which means this is O, this is 3 x O3. Okay. Here I am not going to bother about whether it is 3O or O3, okay. We will just take the magnitude of the distance. Okay. This negative sign will take care of all the other rest. The notion of directions that we have used here have to be retained. Okay. Let us complete this by adding these. There is this force B that is acting, let us say that is acting like this, that is at an angle theta. Again I can find out the perpendicular distance from it and use that particular thing. Alternatively, I can also write this force as two components like this. This is By and this is Bx. In this particular case, given B, I can write By should be equal to B cos theta and this to be B sin theta, where theta is already known. Okay. By writing this, if I take this coordinate, let us say this is 4, I can use the coordinate and write the moment with respect to By separately and Bx separately. Okay. So, I will add that particular part to it and then I will take, I have completed finding out moment for everything, and if I set this equal to 0, I will get a relationship, an additional relationship. I have, how many unknowns do I have here? Going back to this particular diagram, this is something I do not know, this is something I do not know, the magnitude of this is something that I do not know. 1, 2, 3, I should have 3 equations here, 3 independent equations that I should be able to solve. This force equation, which translates into 2 component equations, will give me 2 equations, and the moment equation together will give 3 equations which will help solve these 3 unknowns. And this is all to it in solving a problem with a single rigid body, alright. If it is a multiple rigid body, or a system of planar rigid bodies, we will have to do a few more amendments. I am going to talk about it.